Hi everyone, welcome to this video where I talk about my master's project. I am Kedar Guhan, a grad student at SJSU, and I've been working with Dr. Srikant Jadhav on an FPGA based driver alertness tracker. In this video, I'm going to touch upon the motivation for the project, the methodology, the implementation, and the results out of the project. The motivation for this project comes from the World Health Organization's report stating that the most significant cause of roadways accident worldwide is due to fatigue and drowsiness. Addressing this issue may help reduce the number of such deaths significantly. We studied on various existing solutions, and I'm going to briefly touch upon the concepts developed and used in these solutions. The expressions of a face can be described by identifying all the 68 landmark features in a face. OpenCV's dlib library provides a filter that estimates the 68 facial landmark points. Using these points, the eye aspect ratio and the mouth aspect ratios can be calculated with the formulae as shown in the poster. These ratios are then compared against set thresholds to detect blinking and yawning. Our flow uses another popular and inexpensive approach of applying a Haar cascade classifier with AdaBoost algorithm to identify eye regions and face regions in a frame. This frame is obtained from the camera using OpenCV capture method. Once the eye regions are determined, they are fed to a CNN model which extracts the features and predicts whether the eyes are open, eyes are closed, face is yawning or not yawning. So the prediction model has four classifications as its output. For each frame, these statuses or the predictions are estimated. When both the eyes are seen to be closed continuously for more than 10 frames, then the software triggers an alarm that is intended to alert the driver. The CNN model has been chosen with reduced features to keep the computations minimal while still maintaining acceptable accuracy. The model has been pruned using TensorFlow optimization library, which reduces the features by removing unnecessary weights and neurons. The neurons consist, the network consists of the network consists of three convolutional layers followed by two dense layers. Each convolutional layer has multiple kernels and performs max pooling to reduce the total number of output size. The convolutional layer extracts features from the input image from low level to high level features. The first layer extracts lowest level feature like the horizontal and vertical edges. The next layer extracts higher level features like the curves and shapes. The last layer extracts further higher level features like openness or closeness of the eyes. Some of these kernels don't extract meaningful or usable information, and these are discarded while pruning. These features are then flattened and fed to dense layers to classify into four probabilities. The softmax extracts the highest probability and fixes the final prediction of the frame. The primary dataset used to train this model was obtained from Kaggle, and we have also added custom data with various racial features and lighting conditions to make the model more tolerant to diverse set of scenarios. Also, the custom data that we added were taken from an angle rather than right from the front view. This was to ensure that the camera could be placed on the side away from the driver's visibility or field of view so that it would not block it. And more data set was fabricated by augmenting the existing data set by rotating, shifting, rescaling, and changing the exposure levels of the images. The model was finally trained with a batch size of 50 and 100 epochs, and the training set data includes 1300 images, and the validation data set includes around 580 images. Now, this model inference is the bottleneck on the performance of a solution. So we attempted to accelerate it on the Kriya KV260 system on machine FPGA. For this, we break down the problem into smaller goals. We implement a parameterized matrix multiplier IP that can be used for the dense layers and a parameterized convolutional layer. We first implemented the matmul IP using Vitus HLS, which is a high-level synthesis language based on C++. After simulating and verifying the functionality, we export the IP implementation and use Vivado tool to create a block diagram for our KV260 board. This block diagram interfaces the Zinc processing system with our IP using AXI stream interfaces and DMA to transfer large data between the processing system and the programmable logic. The IP can be driven and invoked from the PS through C APIs. We use Pink library, which is an open source Python library that interfaces with the fabric and is used to program the write overlay bit stream and read or write to the DMA. Then we implemented a 3 by 3 convolutional kernel with line buffer technique. Then we also implemented a scaled it to make it more parameterized, multi-channel, multi-kernel IP with variable input size. This performs convolution followed by max pooling to reduce the output size. Finally, we implement the CNN model on HLS using these blocks. The input image is a memory mapped array which is converted to XFCE image object for processing. The intermediate data flow is done using HLS stream objects. We have also synthesized the entire CNN model without using these blocks and instead using the open source HLS for ML library. And alternatively, we have also explored other approaches like instantiating and configuring the Xilinx's DPU IP and interfacing it with the Zinc processor to generate the bit stream. Now the model should be compiled using Vitus AI to generate the runtime instructions for the DPU IP. Coming to the results, the software implementation runs in real time at 30 FPS on laptops like with Intel x86 processors. But on the Kriya machine, it only is able to achieve about 10 FPS with large latency. The model achieves about 91% accuracy on average over all prediction classes. It does not do a great job at yawns correctly, but it is very accurate at detecting eye blinks. The HLS convolutional kernel is simulated and to verify the functionality. The input size is set to be 512 by 512 grayscale image, and the 3 by 3 kernel is an edge detector which is used. The output is shown on the poster where the rightmost image is the max pool downsized image. The matmul and the convolutional IPs are synthesized. The timing is met up to 200 megahertz and for the 4.8 nanoseconds clock period. This single channel, single kernel convolution operation already takes up about more than 11% of the FPGA LUTs. So a bigger FPGA would be required for the entire CNN model to be placed and routed. We synthesized results for the CNN network using HLS for ML library. The results indicate more than 100% utilization. So we need to find ways to optimize the HLS code using the right pragmas and to reduce the model to be able to fit on the FPGA. This is left as a future work for this project. In conclusion, in this project we have implemented a drowsiness tracker that triggers an alarm based on blink detection and yawns. The prediction is done by a CNN model, which is attempted to be accelerated on FPGA. The model achieves about 91% accuracy in the blink detection, although yawn detection is still inaccurate. We implemented a parameterized matmul and convolutional kernel on HLS, which can be used to implement any CNN architecture. Future work includes optimizing the HLS code and reducing the model to fit on the FPGA. I thank Dr. Shrikant Jadhav for guiding me through this project. Thank you for watching.